Hi, welcome to our talk. I'm Manisha, a PhD student at Machine Learning Lab, IIIT Hyderabad, under the supervision of Dr. Sujit Gujar. Today, I'll be presenting our work on achieving fairness through neural networks. The agenda for the talk is as follows. Firstly, I'll provide the motivation for fairness in prediction models. Next, the fairness definitions that we consider in our paper. This will be followed by the existing approaches versus our approach. I'll then present our network in detail, followed by results and certain bounds. Machine learning based prediction is being used to aid manual evaluation in recruitment sectors for criminal assessment and for loan approvals in banks. Invariably, the predictions from these models are exposed to certain sensitive data like gender, caste, etc. And the model predictions become biased towards these sensitive attributes. Let's say in the training data, we have samples from X that belong either to race A1 or race A2. The model after training is shown to have a high error in the samples belonging to race A2. This may be due to the biased historical data coupled with the training to achieve the lowest error possible. It is our goal to mitigate such bias in any prediction model. In this paper, we consider three specific fairness definitions. Demographic parity, which ensures that irrespective of which sensitive group a sample belongs to, it is equally likely to receive a positive or negative label when the outcome is binary. Equalized odds ensures that the model has equal error rates across groups. Disparate impact ensures the same as demographic parity by requiring the ratio of positive outcome between the groups to be 1. It cannot be compared to DP when the ratio is less than 1. Following a certain discouraging results, it is well known that satisfying equalized odds is possible for a calibrated classifier if and only if the accuracy of the classifier is 100%. We also have similar results for demographic parity. Thus, we have to compromise on fairness constraints while maximizing accuracy since it is impossible to achieve perfect accuracy. We discuss the existing approaches for the same. We broadly classify them into three groups. In the first group are all those approaches which learn representations that do not have sensitive information and hence are fair. These features are then given to a classifier. The learning of representation and classification is decoupled. Hence, the representation may result in reduced performance. In the second group, we have approaches which design convex surrogates for the non-convex fairness definitions like demographic parity and equalized odds, etc. These convex surrogates are introduced in the laws along with performance measures to train the classifiers. Uh, in the fairness constraints cannot be defined per sample and hence are non-decomposable, unfit for standard classifiers. The third set of approaches are based on reducing this task to a sequence of cost-sensitive classification, which can then be solved by a standard classifier. In this paper, we propose a fair neural network classifier FNNC, which tries to overcome the issues in the existing approaches. Our network learns the representation and performs classification in an end to end manner. We do not define any convex surrogates and exploit batch training in neural networks to directly use the constraint in the loss function, hence allowing the training to be carried out for any fairness constraint coupled with any performance measure. We provide experimental results to show that the performance is at par with existing approaches. We also show that our network is generalizable when trained for certain fairness constraints. So, the architecture of our network has two hidden layers and is fully connected with ReLU activation. The architecture can be modified based on the complexity of the data. In this paper, we only consider binary classification. In our loss, we capture the objective of minimizing prediction error while the fairness constraints are satisfied with some approximation. For example, in one of our setting, we train the network to reduce binary cross entropy loss along with demographic parity as the constraint. The binary cross entropy loss is defined per sample and then for a batch of S samples. The constraint is also defined The constraint which cannot be defined per sample is defined for a batch of S samples, and then we allow a epsilon unfairness in our system by introducing this inequality. The overall loss is written with the help of Lagrangian multiplier. The value of lambda varies during training. We optimize our network parameters for minimum overall loss, while lambda is also trained to be such that the loss is increased. Now, this particular optimization is carried out by a two-step stochastic gradient descent at every iteration. We now discuss a few results obtained by FNNC. In this slide, we see the difference of performance across datasets when we train the network with and without fairness constraints. From figure A, we observe that when a network is trained on adult dataset only for minimizing classification loss, there is an inherent bias of demographic parity of 0.16, equalized odds of 0.07, and disparate impact of 0.19. In figure B, we observe that the accuracy is around 87%. But when we train the network to enforce demographic parity to be within 0.01, the accuracy drops to 84%. We see similar trends for other constraints and datasets as well. We also find that higher the inherent bias within a dataset, higher is the drop in the accuracy. So, for example, crimes dataset has an inherent bias of 0.33, hence a significant drop in accuracy from 97 to 83. Whereas Compass has only 0.1 dp, demographic parity, hence a very low drop of 0.2% in the accuracy. We can see that drop for disparate impact is overall is in on average huge, which we later show is not generalizable. In figure 2, we show certain results with Compass dataset for equalized odds as constraints. Here we train our model on Compass dataset where the samples either belong to white or the black race. The error rates before training with fairness constraints vary by more than 5% between races. But when we train with equalized odds as constraint, we see the difference reduces to 1.5%. In here, we compare our approach with Agrawal et al. For Compass and adult datasets. Our network performs well for Compass dataset and obtains 2% higher, 2% less error for the same amount of unfairness in data, be it demographic parity or equalized odds. Although we find our network has 2% more error when trained on adult dataset, it is also found that when the constraint is very strict, our network tends to perform poorly, and we perform better with relaxed constraints, that is, with higher values of epsilon. We also compare our approach with Madras et al., and we find that we obtain 2% higher accuracy on adult dataset for demographic parity and equalized odds. Now, in order to compare with Narasimhan et al., we train our network with Q-mean loss, which is different from a simple classification error, while we also try to ensure demographic parity. From table 1, we see that for all the four data sets, we obtain lower Q-mean loss and better approximation to demographic parity than the three approaches mentioned in the paper. We obtain 0.28 Q-mean loss as opposed to 0.33 and 0.39 from the approaches from the paper, while the DP is within 0.027. Next, we also in the paper we also prove certain generalization bounds. In this theorem, the bounds are proved using the Rademacher complexity. We use covering bounds for neural networks to finally arrive at the closed forms bound. We observe that we obtain tighter bounds when there are larger training batches, but the bound becomes loose when the complexity of the network increases in terms of more hidden layers, which is R, or the number of parameters D. We also prove through the generalization bounds that the disparate impact constraint cannot be generalized. If we have surrogate defined for DI, there will always exist certain instances for which it becomes unbounded. So, to conclude, in this paper, we design a network to ensure fairness while maintaining high accuracy. In future, we would like to extend our work to other complex performance measures and constraints where the data has multiple sensitive attributes and labels. So here are certain references. Uh, Thank you for your attention and please contact for further discussion.